I'm talking today about the first three-dimensional faceted and macroscopic single crystals of the early rare earth oxypnictide superconductors. And as you may know, lanthanum, oxygen, iron arsenide is a very important piece of the pnictide families. And of course, it's important since the oxypnictides differ a bit from the other pnictides to understand their properties. But so far, their in-depth investigation was hindered due to the absence of good single crystals. And this is what I'm going to talk about today. So the pnictides with rare earth and oxygen iron arsenide, they were the first ones reported in 2008, and you can establish superconductivity upon the suppression of the spin density wave with fluorine doping, and then finally establishing superconductivity, as you can see here in this plot. So there are very different families of iron pnictide superconductors, and they all share these iron arsenide layers as building block this building block within the structure. And these families on the left-hand side, so the 1-1, the 1-2-2, and the 1-1-1, they were already grown in early 2008 as single crystals. And then, of course, also in-depth studies were soon reported on those materials. But the problem is that the oxypnictides, they were an exception, and single crystals were very hard to be grown. And the reason here is that the chemistry of these different families is different, because the 1-1, 1-1-1, and 1-2 pnictide superconductors, they're intermetallics, while the oxypnictides are, as already suggested by the name, they are oxides. And for intermetallic materials, you can grow them easily from the melt, or you can also use a high temperature solution growth using metal fluxes and self fluxes. And this actually led to very nice crystals from the very beginning, because these are very powerful tools for the growth of intermetallic materials. But the oxypnictides, they are oxides, and the problem is that the solubility of metals is very low in the typical fluxes and self fluxes that were used for the growth of the 1-2, 1-1-1, and so on. And you need to, for the growth from melt or flux, you need to solve actually both components, the oxide and also the metallic components of these 1111 materials. And this is apparently a problem. So let's go back and have a look what were already reported on the growth of 1111 single crystals. And well, there were some reports, but also some issues. So one report was on flux growth using sodium arsenide with slow cooling, and the authors suggested that you have an intermediate formation of sodium arsenic dioxide, which allows the dissolution of the oxygen and therefore the formation of the 1111 material. The problem here is that the crystal quality, so you see here the full width half maximum, is not very good and not comparable to the other iron-based superconductors or crystals of the other iron-based superconductors, and they were also intergrown with a parasitic 1-2 phase with a very similar TC, shown over here, which was containing both lanthanum and sodium, iron 2, arsenic 2. And this was, of course, also hindering their in-depth investigations. There were reports from sodium chloride and potassium chloride flux, But here you yield only very tiny and very thin crystals. They are also very buckled, as you can see here on the left-hand side. And this is because you are dealing with an ionic liquid, sodium chloride, potassium chloride, which also have a very limited solubility of the intermetallics in there. There have been reports from the Kapinski group, Nikolai Zigadlo, using high pressure, high temperature synthesis. This is shown here on the right-hand side. But here you have very irregular shapes. Also, the growth is rather irreproducible. And you also have formation of clusters of several crystals and also impurity phases. So you can get crystals, obviously, with these methods, but their quality and their size is not at all comparable to the crystals of the other pnictide superconductors. So this is apparently an issue, and we need to go back to the start to tackle this problem. And I had a very gifted PhD student, Rea Kappenberger, who was going back to the initial synthesis of polycrystalline materials of the 1111 compounds. So she was mixing the precursors, lanthanum arsenide, iron and iron oxide, iron fluoride in the stoichiometric ratio. And then she was using a bore mill to homogenize the material, pressed it into pellets, and then did a 3-step sintering process with intermediate grinding and repressing. And if you look here at the microstructure of such a pellet, you see that already some grains are abnormally large at the cost of others. And they are really growing out of these pressed pellets. And this was a very important observation from Rea Kappenberger to learn something on how we could grow large single crystals of 1111 compounds. Because these abnormal large grain growth may happen in many different systems. It's also reported for different systems. If you undergo not normal grain growth, so continuous grain growth, where you have a unimodal size distribution of grains, but if you have a discontinuous, so-called abnormal grain growth, where you get at least a bimodal size distribution, or typically even a multimodal size distribution of grains inside your material. This has been investigated in titanium oxide, barium titanate materials. As you can see in here, where also the crystals grow on top of pressed pellets of the polycrystalline material. And this is not well understood, but there are some, let's say, empirically found criteria that are in favor of abnormal grain growth. And one of them is that certain impurity concentrations trigger abnormal grain growth. It's also beneficial if the system is not in chemical equilibrium. And both factors are actually present in the 1111 polycrystalline pellets. But what is also very important, and this is one of the key here, you need a high anisotropy in interfacial energy. So we had a starting point similar to the classically reported barium titanate polycrystals shown here, where we have already large abnormal grain growth. And now we wanted to trigger the abnormal grain growth even further to get even larger, even better crystals. And then we had different tuning parameters, which I will present in the following. So, as I said, anisotropy of interfacial energy is a very critical factor. We decided to use a solid-liquid two-phase system that enhances the anisotropy of interfacial energy at the interface between the solid and the liquid to trigger the abnormal grain growth. So we used additional sodium arsenide to increase this interfacial energy. But please let me stress here that this is not a flux growth. Flux growth always implies that you dissolve your target material and then you crystallize it at a specific temperature. This is not the case here. We only have liquid sodium arsenide at the operation temperature and solid target material. And this is shown here by a measurement of the enthalpy as function of temperature, red heating and blue cooling curves, where you see sodium arsenide melts at 550 degrees C, and at the operating temperature you are well in the solid state of the target material. Sodium arsenide as the, let's say, inducer for the anisotropy is also beneficial because you have at least the arsenic as another component in your target phase. So, of course, you need to decide on the maximum operational temperature, and one ingredient is that the sodium arsenide is liquid, but the target material is not. But you also need to find the optimal window where you have the anisotropic abnormal grain growth, because if you are too high in temperature, then you have too much entropy, and the facets of your grains become rounded, and these pronounced facets are very important also for your anisotropy, and therefore, if you are too high, you will get back to the normal grain growth, but you need high enough temperature to allow for diffusion controlled processes, but low enough to, let's say, to hinder entropy around the facets. We did this in a very specific series of samples where you can see that indeed the optimal temperature window is somewhere in here, where you can get really large and three-dimensional crystals. And then, since we are not dealing with a crystallization from a melt or from a liquid, the dwell time, so the diffusion time, is really important. And this means the longer you hold the high temperature, the optimal high temperature, the larger and better your crystals. And in our case, we found that at 200 hours, the crystals become very large and three-dimensional. And this is a purely diffusion-controlled process, because if the solubility would play a role here, then the cooling process would matter a lot. Indeed, we can see that slow cooling is even not good for the quality of the crystals, because if you cool down very slowly, you have the growth of parasitic 1 to 2 phase on top of your already grown 1111 crystal. You can remove this material by polishing, and then you really get a clean 1111 single crystal. And this tells us also that your crystal is already fully grown at the highest temperature due to diffusion control process, and only upon the cooling down you crystallize from the sodium arsenide your parasitic 1 to 2 phase. And this is probably also the explanation why Jan et al. Reported growth from a sodium arsenide flux, and actually this was not a flux growth, but a diffusion control process. So if we now put all our parameters together, it turns out that if we have 1111 polycrystals pressed in pellets, mix it with sodium arsenide in a ratio of 1 to 4, put it in such a crucible assembly, and then we have at ambient temperatures solid sodium arsenide, solid pressed pellets. If we heat it up to the melting temperature of sodium arsenide, we get a wetting of our pressed pellets. At 1080 degrees C, we are low enough in temperature to do not allow the rounding of the facets, but we are high enough to have a high diffusion coefficient, and we allow for 200 hours to grow the crystals within the solid pellets, and then we can cool down fast to room temperature. And with that, we get really large, three-dimensional and faceted single crystals of the 1111 materials. Of course, we did a very careful characterization of the crystal morphology using Lauer diffractometry. You can see here the spots on different facets of our crystals. We did a compositional analysis using scanning electron microscopy, both in secondary electron and backscattered electron mode, so revealing chemical homogeneity. And we also did EDX spectroscopy to really probe that we are here dealing with a lanthanum oxygen iron arsenide material. We also did X-ray diffraction on powders using both crashed single crystals as powder, but also single crystal diffractometry. And we are here clear to prove that we are dealing with the 1111 structure that we want to have. If you compare the single crystals and the polycrystals, you can see that the structural and spin density transitions are shifted a little bit to lower temperatures, which may be related to an oxygen deficiency in the single crystals. But nevertheless, the transitions are very well resolved in the single crystal materials, much better than in the polycrystalline materials. You also see the transition for the parent compound very well in specific heat. And you can also do some cobalt doping in here. This is shown on the right-hand side, where you can introduce, so you can suppress the spin density wave and structural transition, but at the same time, you can establish a superconductivity shown in the lower figure here. So this all demonstrates that we have very good sample quality. Of course, if you have single crystals, you want to measure the anisotropies in your material. So you see pronounced differences for the susceptibility along the different crystallographic axis. And we were even able to measure the orthorhombic distortion along two different crystallographic axes in a series of cobalt-doped single crystals to learn something about the formation of the structural transition. Currently, we were successful in replacing the rare earth lanthanum with samarium. So these are the single crystals here. So we needed to modify our growth protocol. And as you can also see here, we see the transition of the structural and the spin density wave phase in the magnetic data, which are very well in good agreement with what has been reported for the samarium 1111 phases. And of course, here we will also play with cobalt doping substitution series. Also, we want to study the interplay of the iron magnetism with the samarium magnetism. And this is what will keep us busy for the next month. We have already done a lot of physical properties investigations in collaboration with many people. You find these studies in these papers in here. And I hope that I could show you that we have really nice, beautiful single crystals of the 1111 phase, that we used a novel approach. It has never been used before for the growth of 1111 materials. And with this, I want to thank all my collaborators, in particular Ria Kappenberger and Sai Aswatham, the organizers of this meeting, the German Research Foundation for funding, and you for your attention. And with that, I'm happy to accept your questions.
Hi, Sabine. Nice talk.
Hi. Thank you.
I have a question. When you add the cobalt in the materials, are there any the size difference in the pure materials and the cobalt samples?
Yes. So you see a very small difference in the lattice parameters. So iron and cobalt, they have very similar ionic radii. So this is tricky, but we can really probe the composition and the structure.
Okay, then I have a short question. Can you apply this method for fluorine dope samples?
We hope so. So far we were not successful, but we have a lot of ideas how to modify the growth procedure to also grow fluorine doped single crystals. Of course, that would be much better because the C is higher, and also you do not disturb the iron arsenide layers. Yes, we have ideas, but it's much more complicated.
Okay, thank you. And Professor Trantner?
Thank you, Sabine, for a very nice idea, and it was successful. So, do you mind that this can be also used for cuprates? Because to grow large crystals there, saying to make same ceramic, and after that place it in the oven and got in saying 200 hours large crystal.
I don't know whether it works with the cuprates. If you carefully check in literature, you see that this is not so rare. So many systems exhibit abnormal grain growth, but there's not much done in terms of really exploring phase space, exploring material space. So let's say the people working with abnormal grain growth have mainly focused on specific materials and not much on quantum materials, but more application related. But I'm pretty sure that this works in much more systems, or that you can also modify a specific system in such a way that you can trigger abnormal grain growth. So cuprates, yes, why not?
Yeah,
I
it's
would
nice.
give it a try.
Yeah, nice. Thank you.